Today we want to check out the cofactor formula, also known as cofactor expansion or Laplace expansion. Looks something like this, a little complicated, so let's break it down into its components. First of all, we need to understand the labeling of a standard matrix. So let's have a look at this 3x3 matrix example. The first number always represents the row and the second number the column. So A11 is first row, first column, A12 first row, second column, and so on. Let's load this sample matrix over here, where in the A11 position we have the 2, A12 position we have the 0, and so on. So let's work with this example and go through the cofactor formula. Okay, so we carry along the sample matrix over here, and now we start with our calculation. So what we do first is we fix the A11 position and we remove all the entries related to the first row and to the first column. So only this part here remains. And we then look at this area over here, which is what we call the minor. And we then take the determinant, that is basically what's happening here. So fix A11 position and calculate the minor, which is just a simple calculation as such, will give us minus 13. And we do the same for the A12 position. So over here we fix this 0 and erase all of the other entries. So see, we have this 0, erase everything else. And we then take the determinant of this minor here. Same thing, gives us 13. And we do the same for the last position in the first row, which is this one here, the A13 entry. Remove everything, get this, and calculate the determinant, give us 13. Okay? And then the next step is to calculate the so-called cofactor. It is calculated using the minor that we just saw, and it's using this formula over here, so minus 1 to the I plus j power times the minor. So what does it mean? Fix it over here as well. This will generate something like a checkerboard, and it will tell us whether we are dealing with a plus or a minus sign. And looking at this 5x5 matrix, we see plus, minus, and so on. It's a repeating pattern that tells us whether we have to add a minus sign or not in front of the minor. Let's look at this. Fixing this checkerboard over here, we then do the calculation. And we already know, like the minors over here, we calculated them. It was minus 13, 13, and 13. And this entry before, whether it's a 1, minus 1, or 1, is defined by this pattern. We have 1, minus 1, and 1, which correspond to these three signs over here. And then we multiply it by the minor to get the end results, these here. Okay, moving on, we can now again look at the original formula, which looked a little bit complicated, but now we can split it up basically. So we see that I and j are representing the row or column entries. So I is representing the row and j is representing the column. And it's used everywhere. So you see it over here, ij, 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 and so on, here as well. And the cofactor calculation is split up into two parts. So we have the minus 1 to the I plus jth power over here, which is the checkerboard basically, and the minor part over here, so mij. And the cool thing about this cofactor expansion is we can do it along the rows, and it doesn't matter which ones. It can be the first, the second, the ith row, but we can also do it along the columns. Basically, you can transpose the matrix and then get the same results going along the rows. So this is what is represented here. This one is here, the j and the I, but it's the same formula. Okay, and now let's check out how it works in our concrete example where we chose the first row to do the expansion, and we get A11, A12, A13, and their cofactors. And we do the calculations, and then we get to minus 13. That is the result using the expansion along the first row. To check that it's really the correct value, we can also confirm it in this small Python calculation over here, where we're using the SymPy library, loading the matrix, the same matrix that we used in our example. And when I do the calculation, just say a.determinant over here, it will give the same result. So minus 13 is the result that we're getting, and it's almost magical that we always get the same number no matter how we split up the calculation as shown before. That's all that I wanted to show you for today. Thanks for watching. Don't forget to like and subscribe, and see you again soon on this channel.